Great, yes. So I'm Allan McRobie. I work here. I often lecture from this stage, teaching structural engineering to the students here. This all started about 10 years ago when Bill turned up here from Chicago, and he said, you need to read Maxwell. And I said, we don't do history. We're an engineering department. We do the future. We don't do history. He said, no, you've got to go get Maxwell's papers, read them in detail, the original papers. And I did, and I was absolutely amazed that there was so much I did not know. Every day was a sort of revelation. You get to my age, you're not being arrogant, but you think you know your subject. You know, you've been teaching it for so long, you know what you know. And there was so much in here I did not know, and I just couldn't believe it. It was just revelation after revelation. So these are some of the things that we sort of found out, and places we've taken it since, having learned stuff. So this talk, we're going to things we've discovered since first looking into Maxwell, and I'm going to put some emphasis on duality. And then for the second theme, and I hesitate to do that, but I'm actually going to say that maybe there's something to do with electromagnetism here, because there's an obvious electromagnetic sandwich between the 1864 structures paper and the 1870 structures paper. These are two big papers that we're really going to talk about. And right in the middle of this structures, this is the classic 1865 paper there. And I think it was Professor Calladine who suggested that maybe when he was doing all this stuff on structures, he was in a sense warming up. He was maybe thinking about it. He was trying to get his head around maybe dualities and things, because he really wanted to make this attack on electromagnetism. So I'll try and say something, but I'm not an expert. I don't know anything about history. I'm an engineer. So graphic statics, there's some classic stuff. Bill's talked about that. This is Bill's notebook. He walks around and he draws these graphic statics pictures, and then he builds them. So those are in Sydney and Chicago. And the amount of material that's saved, because he does it with this very resource-efficient way, because he knows what the forces are, saves huge amounts of material. So just to remind you, Bill's almost said it, there's Varignon 1725. Look at that node Q there. It's in equilibrium. We take those three forces, and you know this from school. If you did science, you can arrange those three vectors, and they form a closed triangle. I'm actually going to colour that triangle in, because it's actually a triangle now. So it's a closed-forced polygon there. And then you stick all these polygons together from all of your nodes, and you've made a diagram, the force diagram. And now let's notice the duality. It's all about duality. Keep your eye on the duality through it. So we started with a node over there, and over here we've now got a polygon. So we go from point to plane, vertex to face. It's a point to a plane, really. So what did Maxwell do that Varignon hadn't done 200 years earlier? Is he popped it up a dimension. Varignon was just drawing lines in 2D. Maxwell says, let's pop it into 3D, solve it there, and then pop it back to 2D. So this was the great sort of leap of Maxwell, was to pop it up a dimension. So, spoiler alert, when I come to do 3D structures, I'm going to pop it into 4 dimensions, and we're going to do 4-dimensional projective geometry. But we'll stick with the earlier ones. So I'm just going to do some mathematical preliminaries, because I didn't actually know a lot of this. I didn't know anything about projective geometry, even though I'm a sort of trained engineer. So this is projective geometry. There's a duality in projective geometry, point to plane, line to line, plane to point. So anything... It's point, line, plane, and then you swap them over and you've got plane, line, point going the other way. And so you can swap the words point and plane, and I'm sorry to teach you this because it is the first sort of line in projective geometry, but I honestly didn't know this, even though I'm a professor of engineering, I didn't know this. 3 planes define a point, swap the words. 3 points define a plane. It's true. I didn't know you could just swap the words and get a truth. Do it again here. 2 planes define a line. Swap the words, what do you get?
2 points define a line.
Thank you. It's 2 points define a line. And lots of people say it wrong. Lots of people say 2 lines define a plane, and they don't. You only swap the words planes and points. Cremona knew this in his book on projective geometry. He actually writes it in 2 columns, and every theorem over there has its dual theorem over there, where he just swaps the words. It's incredible. The whole book goes like that on projective geometry. And I didn't know any of this. But this is exactly the duality we need to do graphic statics. We've got to go from point to plane. This is the geometry I need to do this form and force stuff. So We started doing this. This is some results of some recent research. This is a nice thing where you add your form and your force diagram. You add them together and you get this Minkowski sum, and it goes from the form to the force. It's pretty cool, actually. I mean, structures don't know, my lectures don't normally look this cool. This is in 2D, this is in 3D. And these are the load paths that Bill's trying to optimize here. And this is sort of tells you how much steel you need. And you've basically designed it just by doing this projective geometry. This is some work Marina did, telling you the load path through lumps of concrete. We can do it now on kinematics. The main, you don't need to follow these, just see that it's geometry. I'm doing geometry, there's pretty pictures, there's not equations and integral signs. I'm drawing things. So this is how you do kinematics in 3D. This might even move, the pieces sort of slide around in sort of cool ways. It's doing geometry in ways I've never done geometry before. We could even generalize it now, not just to do pushes and pulls, tensions and compressions. We could do bending moments. I mean, I teach from this stage bending moments. I've never done it this way before with bending area stress functions like this. So this is all new to me. We could even do stability. Someone talked about stability. What about Euler? Well, yes, we can do stability by graphic statics now. There's the Chiasso shed. I can even do it in 3D with moments. So this is the full theory. I've got my full theory of structures now geometrically, thanks to Maxwell. Well, sort of extensions of Maxwell. So let's just go back a bit and say, what was this ordinary sense about a paraboloidal revolution? What's that all about? Well, this is how the polarity works. This is a picture Marina drew. You throw in one polyhedron and you take the points of it, and then each point you work out the plane, which is sort of the shadow. Had that been a light, it defines the plane where all of the rays are tangent. So for the 4 points over here, you get 4 planes. So you go from one tetrahedron to another tetrahedron. You go from that tetrahedron, you can take those 4 planes, you get the 4 points. Or the 4 points, you get the 4 planes. So this total duality, popping back from one to the other. And then you squish them all back into 2D, and you've got your forces and your structure. So why should a polarity of your structure give you the forces? Well, it's a Legendre transform. Well, I didn't really know what a Legendre transform was either, but it turns out it is a Legendre transform. And I'll try and explain what it is. Maxwell knew all about them, but he didn't give any credit to Legendre. He knew Legendre had done other stuff, but maybe, well, I'm not a historian, but anyway. So they apply in mechanics and thermodynamics. And here's what a Legendre transform is. We can all draw a function f of x, and we just plot all the points f for each given x. Or another way to do it is you can draw a tangent and its intercept. Well, it's actually the negative intercept. There's going to be a negative on all the intercepts, but ignore that for now. So I've got this tangent and this intercept. And if we take all of those tangents, the envelope of those will draw the curve. So we could draw the curve by just plotting the intercepts and the tangents. And we can see instantly this, Claire said no equations, but I have put an equation in here. F plus g equals k plus x. And you can see it there that the slope times the length x is that height kx, and that must equal the f plus the g. So that's the Legendre transform there. And so to transform from f and x to g and k, that is a Legendre transform. And k was your slope, and g is your intercept with a minus sign. So it's very easy, linear, y equals mx. Y equals mx plus c, we know from school, that's affine, it's called. Change the sign of the c, stick it over on the other side, same equation, and you've got a Legendre transform. And what's beautiful about this is a beautiful symmetry now, because you've got your y's and your x's, and your c's and your m's. And over on one side you add them, and over on the other side you multiply them. But you can swap them over with this beautiful duality now. You can see the duality in the Legendre transform. It instantly generalizes to higher dimensions, but again you just take the slope, which is now the slope of a plane, and you've got the intercept there. So this is it in 3D. You can see the duality, the white and the yellow, the sum, the Roman and the Greek. It's there. The sum on one side, the dot product on the other. Note the duality. So go back to Maxwell 1870 paper. Using that, he comes up with this thing called a diagram of stress. Looks like a fountain. This is the beam. It's basically Airy's beam that was looking at the Britannia Bridge. He wants to know the stresses in those beams. And Maxwell says, those are the stresses in the beam. that fountain, and I didn't know that. I mean, I'm a professor of structures, I didn't know that. Professor Calladine did, but I didn't know anything about it. So what does this diagram of stress mean? What's that all about from 1870? So he defined this mapping from the body space. So your body space is like a big lump of plate of steel. And then over here you've got this stress space. And he says define a mapping from one space to the other space in such a way that no matter how complicated the stresses are over on the left-hand side, that curve A, the force on it, we're going to replicate over on this side, even though on this side we've only got an idiotic isotropic uniform stress. Even though it's totally simple, we're going to completely replicate that force if you can come up with a mapping. I didn't know any of this. Obviously, it satisfies equilibrium because it's closed on that side. Hydrostatics says it's got to be an equilibrium. And now we'll get moment equilibrium as well as force equilibrium. So to find such a mapping, pick any function, take its slope, its gradient, and plot it over in the stress space. And you can also define the second function, which is basically the intercept, the negative intercept, which is defined by the Legendre equation there. And so let's do that. Let's go back to Airy's beam, and let's actually try it on a beam. So this is like the Britannia Bridge. There's the beam. There's the Airy stress function. Airy didn't draw it in such nice colours. He wrote drew some contours. That's basically Airy's solution. And what you normally do is you differentiate it twice, because those are how you get your stresses, and you plot your stress contours, and that's how stress function works. But Maxwell says, no, don't do that. Just take the gradient, just differentiate it once, and plot the gradients. And if you plot the gradients of the colourful thing, you get the fountain. That's what the fountain was this plot of all the gradients. But we could go further now than that. Well, let's just see how it works. Basically, we can read. You look at the red stripe over there, there's clearly pushing and pulling, and over here we've got pushing and pulling, and you can sort of map the stresses. You can read that diagram once you learn to read it. But we could go further. We could actually plot this extra dimension, the dual stress function, and even Professor Calladine had never seen this one. This is the extra dimension that Maxwell has added. And Maxwell didn't even draw this one. He just drew the fountain, just its projection. But we can draw that one now. And we can compare this with graphic statics. So this is it if I do it in a discrete way for a arch bridge over there, my arch bridge. The force diagram is actually a cable-stayed bridge. We could build one or the other. But we can now draw the dual stress function over it. And you can compare it with Maxwell's and Airy's one, and you can see that one is just a discrete approximation of the other. It also works for other trusses. We can start to understand these. So what we've really come up with is a continuous version of graphic statics. So what the architects do with their rulers, drawing lines parallel, we can now do this continuous version of it. So where did Legendre come in? Where did the paraboloidal revolution come in? Well, let's just say, where do these two worlds collide, these two sort of strange worlds? Well, let's just make the Roman equal to the Greek, and out pops the paraboloid. This paraboloid is the thing, it's the invariant set of your Legendre transform. So we'd really never seen this other side of the equation before, and I don't want to be pompous with this, and it is a bit pompous, but it's a bit like that poem by Keats, on first looking into Maxwell's collected works, when he first looks into Chapman's Homer, and he talks about Cortez, isn't it, looking out across the Pacific for the first time ever. And he didn't just say, hey, look, there's a big blue load of water over there. He's like, there's half the world is over there. We've missed half the planet, guys. We only knew about half the planet. It's all of a sudden we've discovered there's a whole other half of my subject. We've never even looked on this other half of the subject before. So let's go and have a look what's over on this other side of the planet. What else can we discover in this new world? We can discover moments. If you look at it carefully, moments is like, I teach it on this stage, it's when you sort of bend something. I was talking to some mathematicians recently, world-class mathematicians. They didn't know what a moment was, but it's a sort of moment. You can read it off the stress function. You can read it from those graphs. You can just take measurements and it tells you the moments. I teach moments from this stage to the students. I don't do it this way. I didn't know any of this. And it's all there. So that was all 2D, actually. And I'm just going to whistle-stop through 3D. All I really want you to see is it's very, very geometric. And it's kind of beautiful. So let's do 3D graphic statics. Instead of drawing lines to represent your force, you draw a polygon to represent the actual force. The area of that gives you the force in the blue bar. You can stick them together like Rankine did and make polyhedra of forces. And they're clearly in equilibrium because it's a closed polyhedron. So by hydrostatics, it's in equilibrium. And now we can define a stress function over each of those polyhedra. We can stick all the polyhedra together to make a polytope. And we end up with a 4D. We start to do these sort of things. So this is the Rankine version of this. This is all still actual tension. We've not put the moments in yet, but we can do the moments. So now let's add the moments in to get a complete theory. So we're going to pick a Maxwell-Rankine stress function. We're going to consider a 4-dimensional space. And you'll consider that little triangle, which represents a force. And in 4 dimensions, you've got 6 projections. You can do the normal 3 projections or your normal 3 space projections over at the bottom, or you can do the 3 other projections you get in 4 dimensions. So you've got 6 projections. It doesn't need to be a triangle, it can be more general. Let's just generalize. And basically, the total force plus moment is equal to the sum of these. And you can add them if you do Clifford algebra or Grassmann algebra. You can add them, and you end up with the generalized force is this force plus E naught times the moment. And you can represent, therefore, any sort of 6 components of your stress results by a loop in a 4-dimensional space. And the maths all works out. It says if you do the Legendre transform, that's just to show you the maths. And it's pretty, it gives you these pictures. But look at this F plus E naught M. That, to me, just looked like the electromagnetic bivector in a 4-dimensional space. And I thought, that's interesting. I don't know anything about the history of I'm looking at you, I don't know anything about it, but that just jumped out at me there. So my initial suspicion when I started this was it's all about duality of form and force. Maxwell's trying to fit electricity and magnetism together. Maybe he's trying to fit form and force together. No, I was totally wrong. It's not about duality. It's about the unity. He unified them. And so it's this unity of force and moment that's a sort of bit of a pre-echo. That's just me hypothesizing. Maybe you all knew this. Maybe Felix Klein had this all sorted out and you think it's the sort of thing you just spotted. But it looks to me like there's something going on there in this there. So I'll just end with this very quickly. Modern statements of electromagnetism are often framed in a very difficult form of mathematics from algebraic topology called de Rham cohomology. And I think that's how it's all done these days. So can you do something similar for structures? Well, I believe you can. And this is just a click, click, click through them. You try to do this hard math, and I'm really not very good at this. So if there are any cohomologists here, please see me afterwards, because I could do with some help on this. But you can define your structure as a set of loops. You start off with a spanning tree. Every bar node in the tree defines a loop. Dual to that loop is a force loop. It's all about the duality. Equilibrium is given by the wonderful equation, the boundary of the boundary equals 0, delta delta equals 0, which is the key equation in algebraic topology. And that's equilibrium. I'm an engineer, and that means equilibrium. And you can represent it as a chain complex, like so. And I'm struggling a little bit, but you can do your form, your force, and your displacement. And I just end with this, really. This is my penultimate slide. If you multiply together my generalized force and my generalized displacement and take the wedge product of them, you end up with a 4-dimensional volume object called your virtual work. Now, virtual work is kind of sacrosanct. It's the one true truth in my subject. Everything starts with virtual work. It's the one thing you've got. And now I've got a geometrical picture of it as this 4-dimensional object. And that's just... I mean, there's so many books written about virtual work, and no one's ever said before, it's just this 4-dimensional object. I teach this from this stage. I draw that one. That's 3 of the dimensions. The 4th one is you've got to multiply by E naught in that particular case. But it just agrees. It's just really exciting to be able to write down the foundation, rewrite the total first line of the foundations of your subject as a geometrical thing. We can apply it. This is applying it to sort of shell theory. Toby, people who work with Bill are applying it to design fancy shell structures around the world. This is another way you can use it to design grid shells. You come up with a thing in 3D, you pop it into 4D, you then project it back to 3D, and you've drawn the roof. You've designed the roof over there. You've got all the geometry, the faces are flat, and you even know the size of the steel bars just by doing geometry. That's not how I normally design a roof, but this just works absolutely beautiful. So on first looking into Maxwell's collected works, there's just loads of stuff that we've never seen before, and we're still discovering stuff. And so I'll stop there. So thank you very much.